The next thing we're going to talk about is equilibrium and chemical equilibrium. And this also is something that sometimes confuses people based on the name, which is equilibrium. So a lot of times when people see equilibrium, they think equal. So they think you have equal amounts of everybody on both sides. And that's not really the case. So chemical equilibrium involves a specific type of reaction, and it is a reversible reaction. So reversible reactions are the types of reactions that we deal with in terms of equilibrium. We could recognize those reactions because they have arrows heading in both directions. So when you see these arrows heading in both directions, this is a reversible reaction. And there's basically two ways it goes: from reactants to products. That is what is referred to as the forward direction, going from reactants to products. In a reversible reaction like this, at some point you will build up enough products that they will decide to also start reacting with themselves, and will send the reaction back the other way, where products will then form reactants, and that is what is referred to as the reverse direction. So in a reversible reaction, pretty much at the beginning, all you have is the forward direction. So all you have is the reactants making products. And again, you do have to sort of build up enough products that there's enough of those guys to start reacting with each other and basically come back the other way towards the reactant side. So what does it mean when we reach chemical equilibrium? It has really nothing to do with equal amounts on both sides. What it really means is the rate of the forward reaction will equal the rate of the reverse reaction. So basically what that means is just as quick as it breaks apart into products, those products will reassemble and come back the other way just as fast. What that does is it locks everybody into their concentration, wherever they may be at that point, and they pretty much won't change because it's going one way and the other way the exact same. Everything is balanced in terms of that. So just, for example, this guy had 4 and 2, and this guy had 3 and 5. When it reaches equilibrium, they will be able to maintain, if those are their concentrations, those numbers. They won't change because it's going back and forth at the same rate, and they will keep those numbers. The only way it will change is if you do something to it that kind of screws up the equilibrium, which we'll talk about in this chapter as well. So the system is at equilibrium, like I said, when that rate of the forward reaction equals the rate of the reverse reaction, essentially locking everybody into their concentrations, or even pressures. If you're dealing with gases, they'll be locked into their certain pressures at that particular point. Their concentrations or pressures really won't change unless something happens to it that messes up the equilibrium. There is a relationship for these type of reactions that is known as the equilibrium constant, and that is abbreviated with a capital K. And ultimately, to calculate the equilibrium constant, you take the concentration of the products divided by the concentration of the reactants. That is what the little bracket means. Bracket means concentration. And basically what it means is molarity, which is moles per liter, is basically what concentration means. So you take the concentration of the products divided by the concentration of the reactants, and you actually take the coefficients in the balanced equation, and they become like the exponents when you calculate it. So you take those coefficients as the exponents when you go to calculate it. What is the equilibrium constant? Well, the equilibrium constant is one of the few things in chemistry that is simply a number. So the equilibrium constant is simply a number that tells you a couple of things. If you have a really large value for K, when I would reach equilibrium, would I mainly have reactants or products? What do you think? If I have a large value of K, and this is how you calculate K. How would I get a large value? Would the products need to be a large number or a small number? It would have to be a large number, right? Big number on top, small number on the bottom gives me a big number. So if you see a large value for K, what it tells you is when this thing reaches equilibrium, you will mainly have products present. And the opposite is true if you had a small value of K. In order to get a small number, you would need small number on top, larger number on the bottom when you divide, which means you would have more reactants than products, which means when you reach equilibrium, you would mainly have reactants there. So one of the useful values of K, other than just calculating it, is that it could tell you that when this particular reaction reaches equilibrium, you may have mainly products, you may have mainly reactants that are present based on the value. So you may be asking yourself, what is a large value of K? It is pretty much anything over 1. So 1 is the big number there. Anything technically above 1 is considered a large value for K, and you would assume that you would mainly have products there. Anything that is a less than 1, kind of a negative exponent, you would expect to have mainly reactants. There is various degrees of large and small. For example, you could have a large value that is like times 10 to the 39 or 50, which is a very, very big number, as opposed to you could have a K value that's like times 10 to the minus 39, which is a super small value. If you are at any of those extremes, it's almost like a one-way reaction in certain cases if you have a really large value of K. But any equilibrium reaction, regardless if you have a super large value of K or a super small value of K, there will always be some type of back and forth. So there's always reactants and products both in the solution at that time. You just may have like a very, very small amount of reactants or a very, very small amount of products, but you do have both of those things in there. And that's because these type of reactions are kind of like those weak electrolytes we talked about, which have those arrows that kind of go in both directions, and they mainly will stay together in solution. Any questions on that there? So if we look at this for the following reaction, if we wanted to write the equilibrium expression, once again here, we would take our products, which is this guy. So we would take, again, like it shows there, the concentration of NO, and again, we would square it because of the coefficient. And we would divide it by our reactant, which would be N2 times O2. Again, each of the coefficients here are 1, which is why we don't put any exponents. It's just obviously assumed to be 1. Now, as we will talk about with the equilibrium constant, there's actually 2 things that really don't affect equilibrium. And the 2 things that don't affect equilibrium are things that are solid and things that are a pure liquid. So if you have an equation that has something that's a solid and something that is a pure liquid, you do not include it in the equilibrium expression, which basically means there's only really 2 things that get thrown into the equilibrium expression. Those 2 things are things that are aqueous and things that are gases. So anything with an aqueous or a gas, those go into the equilibrium constant. Anything that is solid and liquid, we don't basically include. All these guys are gases, really. The reason we don't include the solid or the pure liquids for a couple of reasons. First off, the solid is a solid, which means if you just think of like a rock in a water, it's just sitting there, right? It's not really doing much. The only way a solid really could do anything is if you dissolved it, and then it would no longer be a solid. It would be aqueous ions floating around, which then can interact and basically participate. Liquid, something that's a pure liquid like water, pretty much the concentration remains constant throughout the whole process. So it doesn't really change. So it doesn't really affect anything. So we don't include those 2 things. Things that are aqueous means that they are in the solution floating around ready to react. So obviously they will participate. And things that are gases are flying around, obviously, with enough energy and ready to basically interact with each other. Any questions on that there? And again, as I mentioned, the 1 is sort of the number there for large or small. And again, if you're larger than 1, there's considered a greater value of K or large value of K, and you would expect more products. And if it's smaller than 1, then you would expect more reactants when you reach equilibrium. On talking about that, what does the value sort of tell us? One of the nice things about K is it is actually one of the few things here in chemistry that doesn't have units. It really is just a number. And the number basically tells us one of two things. If you have a large value of K, it will tell you that when that thing reaches equilibrium, you should mainly expect to see products have been formed. If you have a small value of K, what that means is when it reaches equilibrium, you should mainly expect reactants to be formed in that reaction. What is considered a large value? It is 1 is considered a large value. So anything 1 and above, if you're given a K value for, you would assume that you would have products at equilibrium. Anything less than 1, it would be the opposite. You would expect to have reactants at equilibrium. And again, it's just mathematically speaking, a large number is achieved by having a large top number and a small bottom number when you divide, and vice versa. A small number means you have a larger bottom number and a smaller top number when you divide 2 numbers. All right, so I think we got to here. And again, here are greater than 1, large value, smaller than 1, a more reactants when it reaches equilibrium. Now, if you do happen to hit a K value around 1, that means you pretty much got equal amounts, and it can happen. But in most cases, you'll kind of be one way or the other over 1, but it is possible to get close to it. To calculate the equilibrium constant, you do need to obviously have equilibrium concentrations given to you to put them in there. So if we look at this reaction here, this is hydrogen plus oxygen makes some water gas there, or steam, has a K value of 2.9 times 10 to the 82. That is a giant number. And that giant number means even though this is a reversible reaction, pretty much we would expect definitely products to be there at equilibrium. And with a value that large, even though it is reversible, it is essentially a one-way street here. Almost 100% of everything's going that way. But even in a situation like this, where you have such an incredibly large value of K, and it almost is 100% all going towards the product side, it is still a reversible reaction, which means even if it's a super, super small amount, there is some of it coming back the other way. But in this case, it's going to be very, very little coming back the other way because of the large value that we do see for K. Any questions on that there? All right, so as I mentioned before, big value to the product. Equilibrium lies to the right is what is sometimes referred to. To the right of an equation is the product side. If we have a small value K, equilibrium lies to the left, which is the reactant side. And again, if we do have kind of a value of 1, we're kind of very close to having equal amounts. Again, the only thing that affects the value of K is temperature. So if you do happen to change the temperature, you will have a different value of K. But if you did like 30 reactions and you just did different amounts and you kept the temperature same and you calculated K every time, it should come out pretty much equal every single time that you calculate. All right, so why don't you try one here? Why don't you calculate K based on this reaction and the values given to you? So calculate the value of K, see what you come up with. Okay, let's take a look. So the first thing we want to start with is, and we'll go with this, the gas here, is to write the equilibrium expression here. So our K would be our products. And we would need to square it because of the coefficient that is there. We would divide it by the concentration of A2 and the concentration of B2. Since they gave us the equilibrium concentrations of each of these guys, we could stick it into this expression, and that would give us K that is 0.5 squared divided by our A2 equilibrium, which is 0.25, and 0.25 for this guy as well. That gives us 0.5 squared divided by 0.25 and divided by 0.25 gives us a value of 4 for our equilibrium constant. First off, any questions on the calculation? Would we expect mainly reactants or products in this case? We would expect products. This is considered a large value of K, which means the equilibrium should lie to the right, which means we would expect more products should be formed there when it reaches equilibrium. Any questions on any of that there? Yes, sir. That is, so that's what you use for the exponent. So in general, if you had an equation like this, whatever those sort of coefficients are, they become like the exponents when you put it into this. So they go up on top for each of these guys. So obviously, if the coefficient is 1, you don't, it's just basically to the first power. So you don't have to really write it or anything like that. Yeah. Other questions? Okay. So there we go. That's good. They agree with us. All right. So the next thing we're going to talk about in terms of equilibrium reactions or these reversible reactions is an idea that was known as Le Chatelier's principle. And basically in this situation, what we have is we have a system that is at equilibrium and is perfectly happy, is going back and forth at the same rate. And then we do something to it. We add some type of stress to it. And basically what happens is when you add the stress, you pretty much mess up the equilibrium. And what that means is, you know, when we are at equilibrium, that rate of the forward direction will equal the rate of the reverse direction. So when we do some type of stress to it, it really messes it up. And because it is a reversible reaction, even though you sort of messed up the equilibrium, it's going to want to fix itself and it's going to want to try to get itself back to an equilibrium state. And there's really kind of 3 things that could happen to try to get it back to its equilibrium state. It can do what people refer to as shifting to the right, which basically means make more products. It could pretty much do the opposite, which is shift to the left, which means you would need to make more reactants. And the third possibility is actually one where pretty much nothing's going to happen. Even though you did something to it, there's going to be like no change that will occur. So those are really the 3 sort of options that you have here in a Le Chatelier's principle problem. It's either going to go to the right, it's going to go to the left, or there will be no change that will happen. But whatever it does, it goes to the right or it goes to the left. What's going to happen is after you added the stress, that reaction will once again find itself back at equilibrium. So like number 1 and number 2. So we're a nice equilibrium reaction. You screw it up, it fixes itself by making more reactants or products. It returns itself to that equilibrium sort of change. So what are some stresses that we could do to a system? Here are some stresses that we could do. We could do something with the concentration, which basically means we can either add or remove is pretty much what you could do to that. We could also change the temperature, which also means you can pretty much increase the temperature or decrease the temperature. It's basically your 2 options there. You can change the pressure. Pressure and volume really go kind of together. And this is a lot of times dealing with a gas sort of equilibrium. And you basically do the same thing. You can increase it or you can decrease it. So obviously those are your 2 options for there. So we're going to talk about each of these things and sort of what happens, you know, if you add more concentration, remove or increase or decrease the temperature. So let us start with then concentration and sort of see what happens if we sort of play with the concentration. So looking at concentration here, again, pretty much two things you could do, which is add more. And that means you could add more reactants, you could add more products. And when you add, what happens is it will shift away from the side you added it to. So if you add more reactants, it will cause the reaction to shift to the right, away from the reactant side. If you add more products, it will cause it to shift to the left, away from the product side. If you're going to add more, it's pretty simple. Usually you just like go to the shelf and grab the bottle and you add more into your beaker. That's a pretty simple way of doing it. You just add more of whatever's there. The other thing that could happen is you can remove, and again, you can remove some reactants, you can move some products. When you remove, it will actually shift towards the side you removed it from. So when we're talking about sides, we are talking about, obviously, there's the reactant side and the product side of the equation. In the actual beaker, the test tube, there's no sides. There's no like, I'm on the left-hand side of the beaker, you're on the right-hand side of the beaker. But when we talk about sort of going to the left or going to the right, what we're referring to is the actual balance equation. And again, if we're going to the right, that means we should expect more products going that way. And if we go to the left, we should expect more reactants. So to illustrate this sort of idea here, let's take a look. By the way, how can we remove something from like a beaker that's all solution? Can we just reach in and grab it? Yeah, that's not a, no, you shouldn't really reach in and grab it, right? Because that's not a great idea. And there's no solid there to grab. So one thing that you could do to remove something is you could actually add something to the reaction that actually will make a solid. And so you could add some other reagent to it that will make a solid. And that's important because essentially a solid is not part of the equilibrium. So if you remember, we do not include solids in the equilibrium expression. So if you add something, so for example, if you had like some chloride ions floating around, you could add some silver to them. And that silver and that chloride would come together and make silver chloride, which is a white solid. And that would essentially be like reaching in and taking the chloride out of the solution, and it would no longer participate in the equilibrium because it's a solid. Another way that you can sort of remove something, especially if there are basically H plus or hydroxide in the reaction, is you could add either acid or base to it. And because H plus and hydroxide like to come together to make water, which is a pure liquid. So you could actually make water, which is something you can't really see. Usually when you make water, you can't go, oh, I just made water. It just looks like the same as what you had before. But that's a very common way that we remove something like hydroxide from a reaction, or H plus or from a reaction, is either add acid or base and you will make water. Water, which is a pure liquid, also not included in the equilibrium constant because it is a pure liquid. So again, that would be like removing. So those are the two common ways you could kind of remove something from a solution, make a solid by adding something else that's not there in the reaction, or adding something to really form water, which is typically an acid or base you would do in that particular case. So if we look at this here, let's say we had a system that was at equilibrium. And we'll say we are at equilibrium here. We'll call this guy over here the reactant side, this guy the product side. And let's just say we had somebody jump on here to the product side. What's going to happen is clearly we're going to mess up this equilibrium, right? That's advanced stick figures. There's faces on that one there. So we clearly kind of messed up the equilibrium by adding more products in this case. To fix it, do we need to put more people on the right-hand side or the left-hand side? We would have to fix it by going away from the side we added and put more people over there on the left-hand side. And if we did, we once again can come back to equilibrium here. And we're back to equilibrium. So this is sort of what happens when we add more products. Obviously, if we did the same thing to the reactant side would come down. So we would have to put more people back over on the other side to the product side to do that. Let's take a look at what happens if we ended up removing some people. So we'll start at our equilibrium position once again. And again, this guy's our reactant, this guy's our product. Now, instead of putting somebody on the product side, we're going to say this guy's just going to hop off. When he hops off, what's going to happen is we're going to get this deal, which obviously not a good day over there on that side of the teeter-totter. To fix this, we need to put more people now back on the right-hand side. So in this case, we're actually going to shift towards the side we removed it from. That's going to allow us to come back to equilibrium and make everybody happy once again here. And equilibrium once again achieved here. So this is sort of the idea that happens when we talk about, Le Chatelier's principle. Something is done to that equilibrium. It really messes it up, but the reaction tries to move in a way to counteract the messing up of the equilibrium. And in this case, one way or the other. Any questions on that there? So if I had this reaction here, say 2A plus B goes to C. If I added more A, which way would it go? It would shift to the right. Again, we're adding A, which is right here. When we add, it goes away. AA is a good way to remember that, add away. So we're adding, we'll shift to the right. If I removed B, which way would it go? It would go to the left. Again, when I remove, B is over here. It's going to go towards the side I removed it from. If I added C, it would go. It would also go to the left here. Again, add away. So we're adding on the right-hand side of the arrow, going to cause the equilibrium to shift to the left. Any questions on any of those there? Okay, the next thing we're going to talk about in terms of Le Chatelier's principle is the idea of pressure and volume. And really, both of these guys are sort of tied together. As we'll talk about in the next chapter, we're going to talk about gases. Pressure and volume are related to each other, basically opposites of each other, which means if the pressure increases, the volume will decrease. And that is because in a very small volume, if you've got gas molecules flying around in a very small area, they're going to have a lot of collisions. And it's really the collisions that occur which causes the pressure to increase. So in that very small area, a lot more collisions, we would expect the pressure to come up. And opposite is true if we drop the pressure when we have a much larger volume. So in a much larger volume, everybody has a lot more room to fly around in, which means it's going to take longer for collisions to occur. Because it takes longer for collisions to occur, we would expect the pressure to go down. So if we increase the pressure, which basically means we are decreasing the volume, the real change that's happening here is the pressure is going up, but we have a much smaller volume because of that. So if we wanted to counteract the pressure going up, would we need more gas molecules or less gas molecules in the smaller volume? Let's just say I put a lot more gas molecules in the small volume. Would the pressure continue to go up or would it come down? would go up, right? A lot more gas molecules, a lot more collisions, pressures can go up. If I lower the number of gas molecules in a small volume, we should then see the pressure start to come back down. So if you increase the pressure, which decreases the volume, it will cause the equilibrium to shift to the side with the least number of gas molecules. Now, obviously, that is dependent on the equation you're looking at as to which side has the most gas molecules or the least. You could do that by simply adding up the coefficients on each side for anything that has a G next to it, right? Which means it's a gas. So you can just add up the total gas you got on the left and total ones you got on the right. Opposite is true here. If we lower the pressure, that means we have a bigger volume. So kind of the opposite here. The change that's happening is the pressure is decreasing. So we kind of want to bring the pressure back up. So we have a much larger volume. So we would need a lot more gas molecules in that bigger volume to get the number of collisions up and bring the pressure back up. So it would shift to the side with the most gas molecules. Personally, for me, because these two things are related to each other, I always think about it in terms of volume. So if you have a small volume, you need less gas molecules in that smaller volume. If you have a larger volume, you need more gas molecules. So I remember this relationship of how pressure and volume are related to each other. And again, I just sort of think about it in terms of volume. A smaller volume need less, small less, and larger volume you need more gas molecules. So that's a good way to sort of think about it. Question on pressure or volume here. All right, the other sort of change that could occur or stress that you could do to a system at equilibrium is temperature. And temperature really is related to, really works the same way as concentration. So that's sort of the nice thing about temperature. Temperature works the same way as concentration. Which means if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. Obviously, increase in temperature would be like adding more, and decrease in the temperature would be like removing it. So what helps you decide sort of which way that is? It has to do with what type of reaction you are dealing with. Are you dealing with an endothermic reaction or a exothermic reaction? So if you are dealing with a exothermic reaction, as we've talked about, a couple of things will tell you that. Very commonly in Le Chatelier's principle is they lay up a delta H value and it is negative. Again, the sign doesn't really matter. It's just you see a negative delta H with a reaction, you know it's exothermic. What that means is energy is being given off. And what we think about in terms of exothermic is heat and energy is considered a product. Not 100% correct, but it is considered to be a product, which means if you have a exothermic reaction, you increase the temperature. Which way should it shift? It'd be like add in heat and energy, which means you add to the right, it should shift to the left, right? It should shift away from the side you added it to. And if you decrease the temperature in an exothermic reaction, that would be like removing this guy, which means it should come towards it, and we should see it shift to the right. Any questions on that one there? That also means if we have the opposite situation, an endothermic reaction, our delta H value will be a positive number here. And what we consider heat and temperature and energy as being a reactant in an endothermic reaction. It is a reactant. which means kind of the opposite. If you have an endothermic reaction and you increase the temperature, you are now increasing the reactant side, which means it should add to the reactant and shift towards the product side to the right, away from it. And if you decrease the temperature, that would be like removing a reactant. Again, when you remove, it should come towards it and it should head towards the product side or the reactant side. So it's really important in these type of situations to understand, is the reaction exothermic or endothermic? I would say probably a very common way is they just give you the delta H value. And again, the number is not really important. It is the actual sign that you see. Sometimes they will write like heat into the reaction. So based on which side it's on, will tell you it's exothermic or endothermic. Or sometimes they'll actually just put an energy value on one side of the equation or the other. And again, based on which side it's on, should tell you if it's exothermic or endothermic. Any questions on temperature here? One last thing, which really doesn't affect the equilibrium, but sometimes talked about with Le Chatelier's principle, is the idea of adding a catalyst. I think we might have talked about catalyst, but just to remind you, in case we didn't, catalyst is not a reactant, and it's not a product, and it does not get used up in a reaction. It is really there to facilitate one thing. It's usually there to facilitate speeding up the chemical reaction. And really how it does that is, as we talked about, every reaction has this activation energy between the reactants and the products. Again, it's that hill that the reactants has to climb to get to the products. By introducing a catalyst, it finds some alternative pathway. And what it essentially will do is lower that activation energy. And the result of that is, because the energy hill is much smaller, it is easier, and there's a lot more guys that have enough energy to get up and over to the other side. And what that does is basically usually speed up the chemical reaction in this case. When you add a catalyst, it just gets there faster. There's actually no change occurs. So that is one way you could actually get a no change situation, is if you add a catalyst. Another common thing that is mentioned is if you add a noble gas, for example, helium, neon, or something like that, to a gas mixture, because those things are chemically inert, they won't interact or anything with the other gases that are in there, and it will cause a no change. The third way you could get a no change is what we were talking about a second ago, which is this guy here, pressure and volume. You end up with the same number of gas molecules on each side. So there is no more or less. They got the same amount of gas molecules on each side. That would also be a situation where you could end up with a no change. Any questions on that there? All right, so let's take a look at a reaction here. I'm going to make up, let's do 3A, that's a gas, plus B goes to 6C, delta H positive 325 kilojoules. All right, for this reaction here, tell me, will it shift to the right, shift to the left, or will there be no change if we add more C, we remove A, we decrease the volume, we increase the temperature, we decrease the pressure. Let's also do, let's see here, we add more B, and let's see, let us do those guys right there for now. That's good. All right, so for this reaction, if we do all these things to it, individually what will happen each time we do each of those things. So we are going to start with, first off, why don't we look at what we got going on here. So we got this equation, and we do have a delta H value given to us, which is basically our energy value. Is this reaction endothermic or exothermic? It is endothermic because only of the positives, all you're really concerned about there. That means when we think about heat and energy, should it be a reactant or a product? It should be a reactant. So it would be on our reactant side if we want to kind of put it in there. All right, so I think we got everything we need here to kind of roll through these. We're going to add more C, which means it should shift. It should shift to the left. Here we are adding on the right-hand side. So it's going to shift away from the side we added it to. If we remove if we remove A, what will we end up with? Shifting to. It will also shift to the left. Once again, we always shift towards the side we're removing it from. So it's a. The idea here is if we added more C, for example, we have more products. More products means that they're going to be able to react with each other faster. And that's going to basically kick off the reverse reaction going to the left. When we remove A, which is a reactant, it's like A is like depleted, right? So we kind of have to fill the hole back up. So we need to go towards it to kind of fill the hole back up. So that's why, again, it shifts towards the side we remove it from. If I decrease the volume, which way we're going to go? So if I decrease the volume, that means really the pressure should go up, right? And that's because we have a smaller volume. So do I want more or less gas molecules in the smaller volume? Want less gas molecules. So we do have to look at the equation here to see which side has the less. And it is as simple as each of these guys are gases, and there's a 3 here and a 1 here. That is 4 gas molecules there on the left-hand side. Right-hand side, that is gas, and there are 6 on the right-hand side. So since we do want it to go to less gas molecules in this particular reaction, that would mean going to our left-hand side, which has 4. Any questions on that one there? If I increase the temperature, it should go to the right. So it works the same way as concentration. Since we determined that this is endothermic, we have our heat and energy on the left-hand side. So we're adding to the left, which is going to make everybody go to the right. Really for the same reason, you're adding energy, going to give all those reactants now enough energy to start reacting, going to kick off the forward reaction, which is why it goes there to the right-hand side. If I decrease the pressure, that means what happens to the volume? Volume goes up, which means that's the way we want to think about it. Bigger volume needs more gas molecules. So in this particular case, that would be to the right. And lastly here, if we added more B, it should go to the right as well. Any questions on any of those there? All right. So just going through some of the examples, I think that were in the handout here. We have this reaction, and if we added more CO, once again, adding more of our reactants, going to allow these guys to really start reacting a lot quicker and going to cause that equilibrium again to shift to the right in this case, going to really cause that forward reaction to occur. Remember, we talked a little bit about, what kind of increases the rate of reaction, and that is, the amount of guys that are there. So more guys there, they don't have to go find each other. It's going to really help the reaction occur. Obviously, increase in temperature gives everybody a lot more energy to get up and over the hill to the other side as well. Obviously, here, if we increase CO2, the opposite would occur. We have a lot more CO2, which means they could start really breaking down and heading in the opposite direction there as well. If we removed water in this case, it would come towards the product side. Again, you could think of this as like decreasing the amount. So almost like you made a hole. So you need to come towards that side and kind of fill it back up as you depleted it on that side. And then in this case here, our temperature, once again, we see our delta H given to us. And really the only thing we're concerned with is the positive value. And that is an endothermic deal, which means really our heat is over here. So if we increase the temperature, it'd be like increasing our reactants. Once again, increasing that going to cause the reaction to shift away from it, as we talked about there. And again, as I mentioned, pretty much gives these guys way enough energy, or a lot more of them, enough energy to get up and over to the product side, allowing that forward reaction really to dominate at that point. Obviously, in this case, this is an exothermic reaction, as we see from our negative, which means, again, we can think of heat as being a product, which the opposite is true here, as we just saw. We will now increase our product side, really giving our products enough energy to go the other way, because as it goes in this direction, our products are like our reactants, kind of what's starting to break back down, and we would get it to shift away. In this case here, we would decrease the pressure, which means, I'm sorry, increasing the pressure, which means that our volume would decrease. So again, we want to go to the side with the least number of gas molecules, as we see here, which would shift to the right. And opposite is true. If we decrease the pressure, we now need a lot more gas molecules to fill that hole, because the volume should increase. So bigger volume, more gas molecules when you do it. Any question on Le Chatelier's principle? Here's just a table of basically what we talked about and sort of the changes that occur. Question on equilibrium, Le Chatelier's principle. For us, probably the Le Chatelier's principle is the stuff you should focus in on, I would think, for equilibrium, and how to write an equilibrium expression, and what it means in terms of, if it's a large number or a small number. Question? Yeah. You mean in the react for the delta H value or something like that? Yeah, they will. Or I will, they will, I think. So really, like I said, there's kind of like two ways it's either expressed to you. A lot of times, like we saw here, they'll just kind of give you that delta H value at the end of the reaction. And again, if they don't put a negative sign, you should safely assume it's a positive number. If it's negative, they definitely would put the negative in there. The other way is, like I said, they will just kind of write like a number in on one side, like plus, 30 kilojoules of energy or something like that. And then you can see it's on the product side, you'll know it's exothermic. And obviously, if you had one where they wrote it in like over here, 30 kilojoules of energy plus something, if you see it on the reactant side, you'll know it's endothermic. So yeah, those are the two sort of common ways it's sort of put in there. The third way would be not a number, but just say heat generically or energy on one side or the other is another way to do that. Other questions?